Have you ever tried to measure something really small and you find yourself squinting at a ruler, trying to guess the space between the lines? Well, today we're going to dive into a brilliantly simple mechanical tool that solved this exact problem centuries ago, turning all that guesswork into pure, beautiful precision.
I mean, it seems like a simple question, right? But it's really the foundation of all precision engineering. When you need to be not just close, but absolutely exact, how in the world do you handle those tiny fractions of a millimeter that a standard ruler just can't see?
Look, your typical ruler is great for a lot of things, but if your object ends somewhere between those little marks, you're stuck. Is it half a millimeter? A third? A quarter? Your guess is as good as mine. And for science and engineering, good enough is just not good enough.
And that's where our hero comes in. Long before digital readouts and fancy lasers, engineers came up with an incredibly clever, purely mechanical way to read those in-between measurements with just stunning accuracy. We are, of course, talking about the Vernier caliper.
So here's our game plan for this explainer. First, we'll see why we need to go beyond the ruler. Then, we'll check out the anatomy of a caliper. After that, we'll uncover the Vernier scale's amazing secret, learn exactly how to read it, and finish up with a pro tip on adjusting for something called zero error. All right, so the Vernier caliper is the direct answer to our whole measurement problem. It's a tool that was designed specifically to give a highly accurate reading, with absolutely no guesswork involved.
Now, to really understand how it works its magic, we first need to know what we're looking at. So let's break down the anatomy of this clever device.
Okay, so you've got two key scales. There's the main scale, which is basically a fixed ruler, and then you have the sliding Vernier scale. Attached to that sliding part are the jaws for measuring, and you'll see a slender probe that slides out from the end.
And all those different parts give the caliper its incredible versatility. Those big lower jaws, they measure the outside of something, like the diameter of a pipe. The smaller upper jaws are for measuring internal dimensions, like the inside of that same pipe. And that little probe that pops out the end, that's for measuring depth, like how deep a hole is. It's literally 3 tools in one.
But the real genius, the absolute secret sauce of the caliper, it isn't in its jaws, it's in those scales. So let's uncover how these two intentionally mismatched scales work together to create some incredible precision. First up, just a quick definition so we're all on the same page. A Vernier scale is simply an extra or auxiliary scale that slides right next to a main one. Its one and only job is to help you accurately read the fractions between the main scale's markings. That's it.
And here it is. This is the core trick. The markings on the sliding Vernier scale are intentionally spaced just a tiny bit closer together than the markings on the main scale. Specifically, 10 divisions on the Vernier scale fit perfectly into the same space as 9 divisions on the main scale. This slight, deliberate mismatch, it's everything.
So why does that work? It's pretty cool, actually. It taps into a natural ability our eyes and brain have called Vernier acuity. Turns out we are exceptionally good at spotting when 2 lines form one single perfectly straight line. The entire system is designed to create just one point of perfect alignment that our eyes can't help but find.
Okay, we know there's a mismatch, and we know our eyes are great at spotting a perfect alignment. But how does that actually translate into a number? Let's walk through a quick example. So first things first, we get our main reading. Just look at the 0 on the sliding Vernier scale. You can see it has passed the 5 millimeter mark on the main fixed scale. So we know our measurement is 5-point-something millimeters. That's the easy part. Now for the magic. We ignore the 0 for a second and just scan our eyes across the Vernier scale until we find the one line that aligns perfectly with any line on the main scale above it. In this example, you can see it's the line marked 5. That tells us our decimal value. It's 0.5. And then you just put the two parts together. The main scale gave us 5. The Vernier scale gave us the 0.5. The final reading is 5.5 millimeters. You see? Once you get it, it's just remarkably simple and elegant. So now that you understand the principle behind it, let's turn it into a simple, repeatable process that you can use every single time.
It really is just 2 steps. Step 1, read the main scale. Just find the last whole number, the 0 on the sliding scale, has passed. Step 2, find the single perfect alignment on the Vernier scale. That's it. Let's do another one just to lock it in. Okay, check out this example. Step 1, the 0 on the sliding scale hasn't even passed the 1 millimeter mark yet. So our main reading is 0. Step 2,
We scan along the Vernier scale and find that perfect alignment. Here, it's at the line marked 92. So you put it together, our final reading is 0.92 millimeters. See? Simple.
And now for a pro tip. What happens if your caliper isn't perfectly calibrated? You know, a tiny knock or just some wear and tear can lead to something called a zero error. But don't worry, it's actually really easy to correct for.
There are two types you might see. If you close the jaws completely and the 0 on the Vernier scale is slightly to the right of the main scale's 0, that's a positive error. If it's to the left, that's a negative error.
And here's exactly what those errors look like. On the left, we've got a positive error where the reading isn't quite 0. And on the right, the sliding scale 0 has actually gone past the main scale 0, which means it's a negative error. You have to account for this little offset to get a truly accurate reading.
Luckily, the fix is just some simple arithmetic. The formula is always your actual reading equals your measured reading minus the 0 error. So if you have a positive error, you subtract it. Now, if you have a negative error, you're subtracting a negative number, which, if you remember from math class, means you actually add it back on.
In the end, the Vernier caliper is so much more than just a fancy ruler. It's a perfect example of how a clever design can leverage our own human perception to create extraordinary precision, all without a single battery or electronic part. It really makes you wonder, what other everyday low-tech tools are hiding a little bit of genius right in plain sight?